Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems. We're now at our 13th lecture of the winter 2022 semester at the University of Michigan. I hope everyone had a very nice and an enjoyable winter break, and welcome back to classes for the semester. So in today's lecture, we're going to be talking about a group of algorithms that are known as the bug algorithms. And so these are within the topic of path planning, which you'll remember that we talked about sort of earlier in the semester when we had our first programming assignment. And so before we get into the lecture material for today, I will go ahead and minimize myself so that we can all see the slide content.
All right. So on the topic of path planning and motion planning, the first thing that we're going to talk about today is we're going to go back and briefly revisit the robot control loop that we had talked about earlier in the semester that sort of puts the different pieces together in terms of how it is we would typically go about controlling our robot and how we've been controlling our robots so far in the assignments that we've looked at throughout the semester. So within the typical robot control loop, what we'll typically have is we'll have some goal state that's expressed to the robot that we would like the robot to achieve. So this could be a location in 2D space in the topic of path planning, or it could be a given configuration state that we want the robot to take if it's a mobile manipulator, for example. And so within that, so once the goal state has been given to our robot, we have some decision-making process that's going to produce a policy, pi, which decides what action we would need to take to move from our current state x to this desired state x sub d. And so that higher level decision then is passed to our motion controller, which produces a control force as output that the actual robotic hardware should actuate or sort of perform in order to move the current state towards that desired state. And so this topic of motion planning kind of fits in between or across these two core modules here of decision making and motion control. Right. So ultimately, what our motion planner should do is it should decide how it is that our robot should act in order to achieve some desired state. And so the topic of today's lecture fits within this topic of motion planning. And so in particular, you'll recall from I think the first lectures of this semester that we talked about graph search as being one approach that you could take for path planning, right? And so you'll recall that we looked at a variety of algorithms like depth first search, breadth first search, Dijkstra's, A-star, and ultimately we implemented these for a path planning project. But in addition to these algorithms, there's a number of other approaches that you could take within motion planning. And so the approaches that we're going to be talking about today are highlighted in the first bullet. So they are referred to as the bug algorithms. So bug algorithms 0 through 2, and also tangent bug. And so these are algorithms that are inspired by, as the name suggests, bugs from actual nature. But in addition to these, there's a few other approaches which we'll also look at later on in the semester. So you have sampling-based search. So for example, rapidly exploring random trees is one well-known algorithm which we will look at later in the semester. But in addition, there's also optimization-based approaches, which we've looked at for our inverse kinematics routines. So gradient descent. There's also potential fields and wavefront algorithms that we could consider. But on the topic of bug algorithms, we're going to focus on these four algorithms for today. And so within motion planning, you'll also recall from earlier in the semester, we talked about this distinction between the approaches that you could possibly take to plan out decisions, right? So on one side, on sort of one extreme, you could fully think through solving a problem and be sort of very deliberative in how it is you would decide to act in the world. And on the other side, sort of the other extreme, is you could react kind of instantaneously to changes that you observe in the world. And so these two extremes then make up this trade-off between deliberative planning and reactive planning that we've looked at in this semester. And so you'll recall that typically with deliberative processes, they'll typically follow a kind of feed-forward process, right? Where you'll have sensor input from the world come in, you'll perceive that sensor input to form a state of the world, a perceived state of the world. You'll then plan very thoroughly across the possible actions that could be taken, and then finally you'll produce some actuator output in that process. whereas reactive controllers will typically follow a subsumption architecture, which we talked about, which would typically be implemented with sort of hard and fast rules that, depending on the current sensor input, would then control which actuation output is decided. And so these controllers then would have some hierarchy that gets processed in parallel and ultimately produces, again, an actuation output. So the algorithms that we talked about earlier in the semester, the graph search algorithms, certainly fell within the deliberative planning paradigm. And so sometimes you'll hear deliberative planning paradigms referred to as the sense plan act paradigm, where you'll have some sensor input that then sort of has a feed-forward process to some planning algorithm, for example, the graph search algorithms that we looked at in this course. And then finally, as output from those planning algorithms, you would have some action taken in the world. On the flip side, right, so reactive planning, the core distinction is that in reactive planning, there's no representation of state formally. It gets embedded in this sort of embodied intelligence that's built into the controller itself, where that embodied intelligence is the result of the set of hard-coded rules that are embedded within this subsumption architecture. And so ultimately then the behavior that's produced within the robot that we would observe is that combination of the control output with the kind of embedded intelligence, that embodied intelligence that is within the subsumption architecture. And so we looked at a number of different examples of robots that are implemented both with deliberative planners and reactive planners earlier in the semester. Right? So you might recall, for example, the iRobot vacuum cleaner and a number of other demonstrations that we looked at that distinguish these two approaches. In particular, one approach that you should be very familiar with is your own path planning algorithms, which you implemented as part of assignment 1. And so you'll recall that in this case, it was a very deliberative graph search algorithm that would represent the state of the world and the state of the robot within the graph representing configuration space, and then it could plan deliberatively based on the graph search in order to arrive from location A to a location B. And so in this video here is illustrating a physical robot implementing the same type of graph search algorithms that you had implemented in our Knievel stencil environment, just that it's implemented on a physical platform within the physical 3D world. So on this topic of how it is that we could get from point A to point B, we certainly focused on graph search for those early lectures, but you'll also recall that there was another very simple reactive policy which could also have been implemented. And so that simple reactive policy was actually a random walk policy. So we looked at this demonstration, which is once again included on this slide, where a robot with a mobile robot with a mobile base simply decides to move in a random direction until it collides with an obstacle, and then it randomly picks a new direction and repeats. And it repeats until it reaches some goal state, which in this case is just going to be to escape this kind of enclosed space. And so what we saw when we looked at this example was that even with a very simple reactive policy, you could actually achieve certain goals quite successfully, right? So in this particular case, this random walk policy actually does arrive at the goal, despite having no explicit representation of state or of the goal state within its planning process. And so this would be an example of reactive embodied intelligence that we've considered in this semester. But this kind of motivates a question, which is really the core idea behind the lecture for today, which is sort of what would be a simple deliberative policy, right? So if this random walk policy is a simple reactive policy, could there be sort of a simple deliberative policy that could also be successful in these cases, right? And so in particular, what this policy should do to distinguish itself from that reactive policy is it should encode some representation of the current state and use that in what we call here this simple fashion to achieve the goal state. And so these are the algorithms that we're going to be focusing on today. So for each of these bug algorithms, we're going to assume that the algorithms are operating in a two-dimensional bounded world, which we'll call W, and there's a known global goal location that the algorithms are trying to navigate to, where the distance from the goal location is measurable. So there's some distance function that we can take between any 2 points within this world and get out a distance. And in addition, there are some number of unknown obstacles, which we'll denote with this WO for the world obstacles. And finally, as input to the algorithm, what we have are two forms of local sensing. So we'll have tactile sensing and also a notion of distance traveled. And so the tactile sensing in a physical robot would be modeled by some sort of bump sensor potentially, right, or some sort of distance sensor. So for example, on the Roomba robots, there would be a bumper that would could be thought of as like an on-off switch when it's collided with one of the world obstacles. And so this is somewhat similar and somewhat inspired by the notion of potentially antennas on an actual bug that could detect when the bug has collided with an obstacle in the world. And for the distance traveled information, we can use odometry. So for example, on the Roomba iRobot, or typically on most wheeled robots, you'll have some sort of optical encoder built into the actual wheel motors that could tell you how far the robot has traveled over the course of its current navigation. And so these will be the two forms of sensing that these algorithms have access to. And so given that setup, the sort of purpose of these bug algorithms is going to be to navigate this two-dimensional space and to ultimately find a path that leads from some start location to a goal location. And so the setup here should be pretty familiar from our setup of the graph search algorithms. So in particular, the goal for this bug navigation is going to be to plan a navigation, so to plan a path from the starting configuration, which will be denoted by the Q sub S, and to the goal location, Q sub D. And so this path can include a sequence of what are called hit or leave points, which will be essentially locations on the actual obstacles where the robot or the bug would have collided with the obstacle. And so the hit points will be denoted by Q sub I superscript H to denote hit, and then the leave points, which would be the locations on the obstacles where the robot is no longer colliding or has sort of left the collision with the obstacle, is denoted by Q sub I superscript L. So the I's denote one of the numbers of hit points or leave points that are used by the algorithm. So let's start with bug algorithm 0, where the pseudocode for this bug is illustrated on this slide, along with an example of how the algorithm would proceed. So there's 3 steps within bug 0. So the first step is going to be to start from your starting location and to simply move in the direction of the goal. If you hit an obstacle, you'll drop a hit point. You'll then follow the wall until you can again move in the direction, so the straight line direction of the goal, at which point you would leave the obstacle and drop a leave point, and then you would simply go back to the first line of pseudocode. So then you would simply head towards the goal again, and if you encountered more obstacles, you would follow this same set of rules. And so in this particular example, what we can see is that given this starting location, which is where my cursor is currently, the first step will be to head towards the goal. The robot will then hit a collision with this first world obstacle, so it'll drop a hit point. It will then follow the wall. So in this case, we'll assume that the robot will turn left to follow the wall. You can see it'll follow the wall along with my cursor until it reaches this point where it then detects that it can move in the direction of the goal without continuing to collide with the wall. So it will then drop a leave point, which is the blue dot, and then follow back to the pseudocode of line 1. So it'll head towards the goal, which in this case doesn't result in any more obstacles, and then it'll reach the goal configuration. So one example then of this algorithm implemented on an actual Roomba or iRobot vacuum is shown here. So you can see the robot is moving towards is following the wall, where the approach to follow the wall is essentially like incorporating a slight turn, which is needed for the actual physical robot to actually follow the wall. And then you can see once the sensor bumps into an obstacle, it can then turn and change direction. So one interesting question to ask with each of these bug algorithms, since they are such simple deliberative planners, is essentially what map could cause this bug algorithm to fail. So we saw in this case an example of the bug algorithm succeeding because it was able to find a path from the start node or from the start configuration to the goal configuration. But we could ask in what cases the algorithm would actually fail. And so it's a good example to kind of work through, try and come up with some examples where it would fail. But here is an example of where this algorithm will actually fail. And so the reason for this is that it'll essentially enter an endless loop of kind of following this outer wall within this obstacle that it'll never recognize and never break out of. So if we sort of step through the algorithm, so what will happen is bug 0 will start at the start configuration, move towards the goal, drop a leave point, begin to follow the obstacle until it reaches this point, or even this point where it recognizes that it can move towards the goal. So it'll move towards the goal, and then eventually it'll hit this second obstacle, which is again it's the same overall obstacle, but from the standpoint of the algorithm, it doesn't recognize that. So it'll drop a hit point and then begin following the wall. So as it follows the wall, following my cursor, it'll then reach back around to this original point at which it left the wall earlier, but not recognize that it's returned to the same path. And then it'll just enter in an endless loop. So it would just continually moving around this outer wall without ever recognizing that it had failed. So this motivates us then to make a better bug algorithm that could at least recognize when it has failed. And so one approach that we could take to do this is then the approach taken in bug algorithm 1. So the pseudocode that is illustrated here on this slide is the corresponding pseudocode for bug algorithm 1. And so you'll recognize, to start with, it's very similar to bug 0. So we've made sort of minimal changes. So we're going to still start the algorithm by starting at the start configuration, heading towards the goal. When you reach an obstacle, you'll drop a hit point. You'll begin circumnavigating the obstacle, where you'll set leave points that are, for basically each point along the wall that you visit, you'll check if it's the closest point to the goal that you've seen so far, and you'll update your leave point based on the closest point seen so far. And then once you've circumnavigated the overall obstacle, so once you recognize that you've reached back to your hit point, you'll then go and re-navigate towards the leave point that you set, which you'll know will be the closest point to the goal. And then you will go back to step 1. So at that point, you'll then leave the leave point and head towards the goal and continue this process. So let's step through and look what this will look like. So in this particular example, the robot will start in the starting configuration, head towards the goal. It'll drop a hit point once it reaches the obstacle and begin circumnavigating this obstacle. So it'll circumnavigate the obstacle, and at each point, it's going to check if its current point along the wall is closer to the goal location than any other point it has been at. And so in this particular case, it's going to update its leave point based on that. So in this case, as it circumnavigates the obstacle, it's going to recognize that this position right here, this configuration, is closer to the goal node, which is this green point up here, than any of the others it's seen. So it'll drop the leave point here, continue circumnavigating until it reaches back to its hit point. So once it reaches back to its hit point, it'll recognize that it has fully circumnavigated the obstacle, so it can move on to step number 3 in the pseudocode. So it'll now aim to return to its leave point. So it's going to circumnavigate, back to the leave point here, at which point then it's going to go back to step 1 in the algorithm. So it's going to now head towards the goal. Once again, it reaches an obstacle, so it'll drop a hit point, begin its circumnavigation of the obstacle, keeping track of which point is closest to the goal as it goes. So in this case, it's going to leave a leave point here, continue circumnavigating until it reaches back to its hit point, and then once again, reach line number 3 now in the pseudocode, so it's going to return to the leave point that it's set, and then finally head towards the goal and arrive at the goal. But as as I kind of foreshadowed with accidentally hitting the next slide button too early, it turns out that even with this change, bug algorithm 1 still might have failure cases. So depending on the map, there's a potential that bug algorithm 1 won't recognize that it's unable to find a path. So one thing that might be good is to maybe pause the video here and see if you could think through about what map could trip bug algorithm 1 up. And so we'll move forward. So it turns out that this would be an example of a map where bug algorithm 1 would not recognize that there's no possible path. So it would enter an endless loop. And so what we can do is we can try and improve bug algorithm 1 by adding some additional logic to detect when it has actually entered an endless loop or when it won't be able to find a path, and to recognize that by returning some notion of a failure state. So it's able to at least detect that it would not be able to find a path without expending additional sort of energy or resources, right? Computing resources, for example, searching. So in particular, the logic that we've added is highlighted down in the pseudocode line number 4 here. And so essentially what we're going to do is we're going to have the algorithm check whether the leaf point that it sets based on the shortest distance to the goal, if that point still results in the obstacle bumping into the, if that point still results in the robot bumping into the obstacle, then we can return failure because we'll know that there's going to be no path leading from that point to the goal. And so this is a way that bug 1 could at least detect this notion of a failure case. So a couple of good kind of questions to work through then is to try and calculate what the best case and worst case search bounds for bug algorithm 1 would be. And in particular, what we can calculate these bounds in reference to is the variable d, which denotes the straight line distance from the start configuration to the goal configuration, and these variables p sub I, which denote the obstacle perimeters that the algorithm will encounter on its path to the goal. So I'd recommend you pause the video here and check your understanding by trying to work through each of these cases. So in particular, the best case for bug algorithm 1 is going to simply be the straight line distance from the start to the goal, right? So the best case is going to be a path of length d, just that straight line from the start to the goal. And the worst case, meanwhile, is going to be d plus 1.5 times the sum of these obstacle perimeters. And so the reasoning behind this is we're going to still have essentially the straight line distance that the bug algorithm will take from the start to the goal. But in addition to that, the bug algorithm is going to have to circumnavigate each of these perimeters 1.5 times in the worst case when it essentially has to return to the set point that it leaves as it does its wall circumnavigation. And so this is how we arrive at this worst case bound here. And so based on this, then one thing that we could ask now that we've looked at bug algorithm 0 and bug algorithm 1 is whether or not we could come up with a faster bug algorithm, faster in terms of the worst case distance here that we're calculating. And so this then leads to bug algorithm 2. And so the pseudocode, once again, is going to look pretty similar to the two algorithms that we've seen so far. But in bug algorithm 2, what we're going to do is we're going to incorporate this notion of an M line, which represents the straight line path to the goal. And so in particular, we're going to use this notion of the M line when the algorithm decides whether or not it should abandon its wall following or continue with its wall following. So the pseudocode is shown here on this slide. And so if we step through what this is going to look like for this particular example, so we're going to start with the robot in the starting configuration. We're going to head towards the goal along the M line. We're going to then hit the wall, so we'll leave a hit point and begin traversing the obstacle, and here's where the change is, until we reach the M line once again. So you can see at this point we've reached the M line. So we're going to set a leave point and exit the obstacle. So when we exit the obstacle, then we'll go back to pseudocode line number 1 by heading towards the goal along the M line and repeating. So then we'll hit the obstacle here, we'll leave the hit point, begin traversing the obstacle until once again we reach the M line, and then we'll once again follow that M line until we then finally reach the goal location. And so once again, we could ask, while this seems like it found a shorter path in this case because we didn't have to do as much traversing of the obstacles, should still ask whether or not this algorithm would fail in certain cases, and it turns out that it would. So in particular, this would be a case where bug algorithm 2 fails. So I'd recommend actually pausing the video and trying to work through yourself. Just follow the pseudocode just to make sure that you're understanding the algorithm here. But if we step through what this one is going to do, so the start location is up here at the top, and the goal location then is the one down at the bottom, which is a reversal of what we've been looking at up to this point. So what's going to happen is, so we're going to start with the robot moving towards the goal along the M line, and then once it reaches the obstacle here, since we're assuming that the robot is going to turn, let's say, left with respect to its forward heading, the robot then is going to turn and begin following the wall until it reaches, once again, the M line, which it will do right up here, and then it's going to again move towards the goal along the M line. So then it's going to remove towards the goal along the same path that it took without recognizing that it's along the same path it already took. So then it's just going to enter this infinite loop that it never detects and ultimately will not succeed at, and nor will it be able to identify that it is in this failure state. So to avoid this particular failure case, we can add some additional logic to our algorithm, which is highlighted on this slide in pseudocode line number 2. So in particular, what we're going to do is we're only going to decide to refollow the M line if we're closer to the goal than we have been before. So in this particular example, the yellow line that's illustrated showing the robot's path is really considering a robot that would turn right at the obstacle. So if we instead consider the exact same case that we looked at on the last slide, what would happen is the robot would start in its starting configuration, move towards the goal along the M line, hit the obstacle where my cursor is currently, and then turn left and begin heading around the obstacle. And once it reaches the M line above the start location, it would not decide to follow it in this case because it's not closer to the goal than it had been previously. So it's then going to continue traversing around the obstacle until it once again reaches the M line here, and it is closer to the goal location than it had been previously. So then it will choose to set a leave point and exit the obstacle, and then continue on. So by adding this logic here in pseudocode line number 2, we've at least fixed the case of an infinite loop due to its choice of when to follow the M line, but we still might have the case of when the algorithm is within an enclosed map or within an enclosed obstacle and there truly is no path. And so we still want the robot to identify that as a failure case, which we can do by adding, yet again, some additional logic. And so in particular, this is somewhat similar to the logic that we added in the case of bug number 1, when we had bug number 1 able to detect failures. Where essentially what this additional logic is, which is highlighted in pseudocode lines number 2 and number 3, what it boils down to is essentially if the algorithm is traversing the obstacle and it recognizes that it has returned to one of its hit points, it will then recognize that as a failure case and report it as a failure case. Otherwise, if it does not reach one of the ith hit points, it will recognize that as a valid leave point and then exit the traversal loop and re-head towards the goal on the M line. And so this will allow it to detect failures like the one illustrated on the example on the left-hand side. So we've looked at a number of these algorithms. One question that you might be having is whether or not bug 2 is actually better than bug 1, because that was originally the question that we set out to really address, was to try and make a slightly more efficient bug 1 kind of variant when we talked about bug 2. So let's compare the two in a few examples. So in particular, let's try considering worlds where bug 2 would beat bug number 1 in terms of its efficiency, and vice versa, where bug 1 might actually beat bug number 2. So in particular, we could look at this first case on the left as being one example where bug 2, which has the path highlighted in red, the more direct path, will actually beat bug number 1 in terms of its path length. Whereas the example then shown on the right is, believe it or not, a case where bug algorithm 1 will actually beat bug algorithm 2 in terms of its the efficiency of its resulting path when applied to this scenario on the right-hand side. And so some kind of general characteristics of these algorithms that would lead to better or worse performance depending on the environment that they're in. So for bug 2, it's a greedier algorithm because it uses that M line as a sort of guiding line. So typically in environments where greedy performance would be beneficial, bug 2 will have better performance. Whereas bug number 1 does a more exhaustive search. So for cases where a greedy approach will have penalization, which is the case on the right-hand example, then bug number 1 can be beneficial and have more predictable performance. So an interesting case to look at is this case here, where we mentioned that bug number 1 will beat bug number 2. And so the reason why bug number 1 will beat number 2 is that bug number 2 ultimately is going to have to essentially loop back, sort of backtrack many more times ultimately than bug number 1 does. So I'd point out this is a great time to pause the video and sort of work through both algorithms stepping through this particular environment just to check your understanding, and then to base that analysis on the best case and worst case performance that we can calculate for bug number 2. So in particular, what we can do is if we express the distance to the goal as the variable d, the obstacle perimeters that the algorithm will encounter as variables p sub I, and then n sub I as the number of m-line intersections for the world obstacle indexed by I, we can calculate these best and worst case paths. So in particular, the best case is going to be length d. If there are no obstacles, right, then it'll just be that straight m-line distance to the goal. Whereas in the worst case, the distance is going to be d plus the summation over the obstacles that it will encounter, where you take the half the number of total intersections for that particular obstacle multiplied by the obstacle perimeter. And so if we look at why it is that this ends up being the worst case performance, essentially this algorithm is going to have to consider all of the leaf points on the m line where only half of them are valid. And so that's where that resulting n over 2 factor comes in. And so each leaf point might ultimately require traversing the entire obstacle perimeter. And so that's where then those obstacle perimeters are incorporated in the worst case calculation. So one way that we could further improve these algorithms would be to extend our notion of the robot by including additional sensor information, with the thinking that if we had additional sensor information, like a range sensor, then potentially we could make a more capable bug algorithm. So let's consider the case where we do have a range sensor on our robot. And so in particular, the algorithm then that we can develop is what's referred to as tangent bug. This is one form of algorithm that's still within the bug sort of family of algorithms that incorporates range finding information as part of its local sensor information. And so in the context of a physical robot, what this rangefinder will typically be implemented in terms of hardware is with what's called a laser rangefinder. And so a laser rangefinder works on the principle of essentially emitting a beam of usually light that reflects off the surface of obstacles in front of the beam of light. And then based on the time it takes for that reflection to come back to the sensor, you can calculate the distance of that obstacle from the location of the transmission. And at that point, then you could build up a map of these distance ranges. And so illustrated on the left-hand side of this figure would be an example rangefinder on a robot similar to the iRobot Roomba vacuums. And then the principle is illustrated here graphically, where you'd have sort of a spinning mirror that would reflect these lasers that would bounce off of obstacles and come back to the emitter for the distance calculation. And so what you can do with these laser rangefinders is you can build up what's called an occupancy map. So these would let you perform algorithms including simultaneous localization and mapping, which is one of the algorithms that's looked at in some of the robotics and computer science courses here at the University of Michigan. So for example, in Robotics 550 or EECS 467, you would have practice building up these SLAM maps, these occupancy grids, which are shown on the right, using these robots shown on the left. So an example of a former student that implemented one of these SLAM algorithms is shown here. So as the robot, you can see, moves around the maze, it's able to build up this map of the environment using these laser rangefinder sensor readings, where the map is then constructed as this occupancy grid shown on the right. But for our purposes, for tangent bug, we're not going to necessarily need to build up this complicated map, but instead what we're going to do is we're going to use this laser rangefinder information to inform our path planning. And so the way then that we're going to do that is we're going to base our search on a heuristic, somewhat similar to the A-star heuristic that we looked at during our graph search algorithm discussion earlier in the semester. And so for this, let's first build up some notation that'll be useful for describing the algorithm. So in the figures that we look at, we'll consider the current state or the current configuration of the robot to be denoted with X, and the goal configuration of the robot to be denoted by this Q goal. So within the environment then, within the 2D environment that we're assuming, let's consider the case where we have visible obstacle extents denoted by O sub I, where the I indexes different obstacle extents. And so these obstacle extents then are shown here graphically. So these are essentially the endpoints of sensed obstacles that are visible. And based on those, we can calculate the distance from the current configuration of the robot to each of those extents, which will be denoted by this distance function here. So these are the collection of object extents that the robot can see and the distance to them. And in addition then, what we can calculate is the distance between these obstacle extents and the goal configuration of our robot. And so this would be representing essentially the best path that the robot cannot see, but it's the best possible path that the robot could take from these obstacle extents to the goal. And so the idea behind this heuristic search is we're going to essentially choose which obstacle extent to move towards to minimize the heuristic then that's shown above. So the thinking is that if we continually move the robot such that this distance to the goal is decreasing, then we'll ultimately be able to reach our goal. And so this is similar thinking to the concept behind A-star search, which you'll remember from our earlier assignment. So within this heuristic, there's two components. So we have this first component, D, so the distance between the robot configuration and extent I. So for example, this red segment, which is shown where my cursor is illustrating this distance between X and the O sub 2 extent. Whereas the second component within our heuristic is then illustrated in the second segment where my cursor is. So it's the distance between this obstacle extent O sub 2 and the goal. So let's then look at what this heuristic might sort of look like for a few different potential obstacle extents that a robot could move towards. Right? So potentially, in this case, our robot can see obstacle extent O1, obstacle extent O2, obstacle extent O3, and obstacle extent O4. So for O2, it would calculate the heuristic as this distance from its current configuration to O2, which is here, plus the distance from O2 to the goal, which is then shown here. Conversely, when it considers whether or not it should move instead towards the obstacle extent O4, it can calculate the distance from its current configuration to O4 plus the distance from the configuration O4 to the goal, which is this shorter segment. And so then based on comparing these, it can decide which obstacle extent it should move towards under the assumption that it can't directly see a straight line path to the goal. And so before it can ultimately take these calculations, one thing that it has to be able to do is actually segment the raw sort of sensor information that it receives into these extents. And so typically these range scans are going to be sensed along a particular ray angle with some distance limit. And so what it can do is it can segment these collection of rays to form basically discontinuities that will distinguish which rays correspond to obstacle extents versus which rays correspond to free space. At least free space with respect to this range limit R. So you can see all of these rays, for example, have reached their range limit, and so correspondingly they're perceived as being directions of free space, whereas the discontinuity between the ranges that have reached their limit, and these ranges that are shorter than their limit correspond then to obstacle extents. So these red highlighted rays correspond to the essentially detections from this sensor that would represent the obstacle extents that our algorithm is going to be using. And so these interval discontinuities are then how you could perform this segmentation efficiently. And so based on that, right, so based on this process, which for the bug algorithm we can assume is given to us, we don't need to go as low level as implementing this ourselves, but based on this, we'll have this collection, this discrete set of segments, which in this figure are denoted by this O sub 1 through O sub 10, that denote these extents that the algorithm should consider traveling towards. So the bug algorithm behavior is going to ultimately, this algorithm is going to follow sort of two potential types of behavior. So it can either move in a straight line, which is going to be when it tries to move straight line towards the goal. So on the left hand, for example, if there's a robot where my cursor is currently, and it has a sort of short range, so it can't see all the obstacles, it'll initially just move in a straight line distance towards the goal until it begins to observe the obstacles, denoted by this dashed circle, denoting the range of its sensor. And at that point, then, it would follow, it would essentially do wall following behavior, so boundary following. So at that point, once it can view obstacles, it'll then decide to follow the boundary in an effort to move ultimately towards the goal. And so the pseudocode for the tangent bug algorithm is what's shown on this next slide. So at a high level, the two types of motion and the two types of behavior that the algorithm will ultimately follow are broken into the pseudocode line number 1 and pseudocode line number 2. So when the algorithm is in the motion to goal behavior, which is what it will start in, the action taken is going to be a move towards the current obstacle extent that minimizes the heuristic function g, and you're going to continually perform this motion to goal behavior until either you reach the goal or until this heuristic begins to increase, which indicates you've reached some local minimum within the map. At that point, if you've reached some local minimum, you're then going to move into behavior number 2. So you're going to begin to boundary follow. And so just as a while loop, you'll simply follow the boundary using the strategy of the bug algorithms that we've looked at before. But during this wall following behavior, what you're going to do is you're going to repeatedly update these three variables within 2a. So you're going to have a d-reach variable, which represents the minimum distance between the goal configuration and your currently visible object extent, O sub I. You're going to have a d-follow variable, which represents the minimum distance between the current goal between the goal configuration and your overall sensed world objects, which are indexed by this WOJ. And then you're also going to update at each step of this boundary follow loop the visible O sub I, which is the visible object extent that you're considering within the d-reach variable calculation, where O sub I is defined as the argmin, so basically the obstacle extent sub I that minimizes this heuristic between distance of the current robot to O sub I and the distance of O sub I to the goal configuration. And so you're going to repeat this boundary following process where you update these three variables until either you reach the goal, the robot has cycled around the obstacles, so you can recognize a failure case similar to how we did in bug 1 and bug 2, or until this d sub reach is less than d sub follow, which indicates that you're outside of a local minimum, and you can then return to your motion to goal behavior. So then you'll exit step 2, go to step 3, which sends you back to the start of the pseudocode. So let's look at what this pseudocode would actually perform in the example that's shown on the left-hand slide. So given the starting location of the robot X, the first thing it's going to do is it's going to perform the motion to goal behavior. So it's going to consider for each of the obstacle extents that it can view, which is O sub 1, O sub 2, O sub 3, and O sub 4, it's going to choose the obstacle extent to move towards that minimizes the heuristic, which in this case, we can sort of visually inspect that it's this segment highlighted in red where my cursor is pointing to. So it's going to be the segment from the current configuration to obstacle O sub 2, and then from O sub 2 to the goal. So that indicates to the robot that it should move towards the obstacle extent O sub 2. So it's going to take that as the first action, which then will position it at the current state updated here on this slide. And once again, it's going to perform this motion to goal behavior. So it's then going to consider between obstacle extent, this new O sub 1 and O sub 2, and decide to move towards O sub 1 because it has a shorter heuristic. So it will do that, and then it would finally have been able to reach the goal in a straight line path following that. So moving on, let's look at an example of this algorithm's behavior when the laser rangefinder is used within the algorithm. So for this example, let's assume that the laser rangefinder has infinite sensing range. So to some extent, this is sort of like having a fully observed environment, where the algorithm is going to sort of begin stepping through the pseudocode that we just looked at. So the first thing to note is that in this case, when the sensing range is at infinite range, the goal location T is essentially known. And so that's sort of the behavior that we'll ultimately see, is it'll sort of move in a very efficient path towards this known location. But to start, it's going to start in the motion to goal phase, where it's going to consider the obstacle extents that it can see from the starting location here, which are these three highlighted in red and yellow, and it's going to choose to move in the direction of the extent that minimizes that heuristic. So in this case, it's going to be to this extent here, which is represented by this hit point 2. So it'll move to hit point 2, and then it'll once again stay in the motion to goal phase because it hasn't observed the heuristic increasing. And once again, it's going to pick to move towards the obstacle extent which minimizes that heuristic, which in this case is represented by this hit point 3. So it's going to move to that point, and then once again, it's going to perform a motion to goal, which ultimately brings it to this point here, where it is here at X. And at this point, it's actually going to move sort of tangent to the object in order to take a step. But what that's going to do is it's actually going to increase the heuristic. So at this point, the algorithm would enter the boundary following behavior, and it's going to start following until it reaches some state that either the goal state, it'll iterate around it'll sort of traverse around the objects, indicating that it can't find a path, so it'll fail, or until the distance reach variable here is less than the distance follow variable here. And so it'll start this boundary following behavior and move towards move along the wall until it actually reaches this point D3, where this D reach variable is in fact less than D follow, where the D reach is indicated by the distance from D3 to the goal. So it's this distance between the goal and the currently visible object extent, which by the time it reaches this position here will be D3. That distance is going to be less than the distance from the goal to the sensed world object over the set of world objects that it's seen, which is going to be left at the local minimum where it was initially found towards where my cursor is currently. And so at that point, it would end the wall following behavior and move back towards motion to goal behavior, which would ultimately result in a straight line path at that final segment to the target, indicated by this segment here. So another interesting example then is sort of the opposite extreme, when the rangefinder has zero sensing range. So let's step through this case and look at what happens. So initially, the algorithm is going to enter using the motion to goal behavior. So it's going to move towards the goal initially. It's going to hit this first obstacle. It's going to have boundary following behavior once it hits the first obstacle, and kind of continually for the second obstacle until it reaches the third obstacle. And so an interesting case happens at the third obstacle where it reaches a local minimum. So it'll have this hit point here, H sub 3. It'll begin boundary following until it reaches a local minimum where the heuristic then starts to increase. So this M sub 3 denotes a point of local minimum for the heuristic function. But the algorithm is going to continue wall following until it reaches the condition where D reach is less than D follow. And so to illustrate this path here is illustrating this continued boundary following because it's in a local minimum. But then to illustrate the breaking condition, or what causes this local minimum to be exited, is shown on this slide here. So the D follow variable is left to be this distance between the goal configuration and the WO sub j, which is left once again as the obstacle extent at which the local minimum was first encountered, whereas the d-reach variable is updated throughout the wall following behavior. So the d-reach variable is going to be updated ultimately to be this point, or is going to be updated to be based on this point that it reaches here, which has a distance between the goal and this obstacle extent, which is sort of like an infinitesimal point located at the current robot configuration that's also in collision with the obstacle's boundary. And so visually we can see that at this point this d-reach is in fact less than d-follow, and so that then is what causes it to break out of the boundary follow behavior and move back towards the motion to goal behavior, which will then result in the final kind of sequence within the path planning, which includes another boundary follow behavior, which is very similar to the first one that we stepped through. And so working through some of these examples, it is good practice to kind of make sure that you understand these cases. So an additional case which we didn't step through but you could consider would be a case where the tangent bug algorithm is applied with some limited radius, which is not zero, but also not infinite, and to consider how that would affect the behavior. And so then as a final kind of concluding point, one thing that is useful to think about is some of the distinctions between the bug X algorithm, so the bug 0, 1, and 2 that we looked at, versus the random walk. So in particular, what does bug X assume, or what does bug X have access to that the random walk does not have access to? So you can pause the video and try and recall. But in particular, the key distinction is localization information, right? So the random walk had no access to sort of localization. It just used that bumper sensor, whereas the bug algorithms assume that they can localize themselves within the map, right, based on the starting location and as they record odometry data. Another then useful question is to consider what the graph search algorithms that we looked at earlier in the course assume access to that the bug algorithms do not. And so in this case, the answer is that the graph search algorithms, of course, by the name, they require a graph of valid locations that are valid with respect to collisions in configuration space. And in addition, they need to be able to build up this graph. So they're going to require additional memory. And the bug algorithms that we looked at do not have this capacity. So with that will conclude our lecture today on the bug algorithms. One thing I want to mention is that, so for our next lecture on Wednesday of this week, we're going to be talking about configuration spaces and the properties that they have and the relation that they have to our robots. And so with that, thank you for watching, and I look forward to seeing you in lecture and discussion section this week.